Today we're going to walk through series circuits. I want to tell you how they work, how we do the math with them, and what kind of drives them, what happens, and what series means. When we really need to wrap our heads around this, we have to understand what resistance does to a circuit. And that it's the boss of the current. The resistance is the boss of the current. Now, how much pressure we have in the system? Yeah, I'm calling it pressure, but it's really voltage. How much voltage we have in the system is actually how much kind of pressure or push we have from the actual battery that's pushing the electrons. But the resistance allows for a certain amount of flow in a circuit. So let's just draw a series circuit and walk through some components. Now, for any series circuit, we need some kind of battery or source that's actually giving us the pressure or the voltage that's pushing the electrons, or the charge, the coulombs, right? So we have this, and then of course we want to put a fuse in our circuit, and it's always good to put control in the circuit. So just throw those components in any circuit you're building because they're pretty important. So let's actually put some loads in here. What I'm going to do is I'm going to use a resistor and a light bulb. So I'll draw those things in. That's going to be my R1, and then I'm going to do a little squiggly here and come down here. Now that's a complete circuit. We're going to label that L1. This is R1, this is switch 1, and that's my fuse. So we know that my VS, that's where the voltage source comes from, and that's what's pushing the electrons. So the charge is going this way. Now we know from conventional theory the current goes like this through my circuit. These guys have resistive nature to them. We want to know really how much current they will allow to flow. Again, the load is the boss of the current. Now, the thing about these guys is because they're connected in series, that means that the current has to go through both of them. Check it out. If I'm the electron, I can go through the fuse, I can go through the switch because it's closed. When I get here, I'm being pushed into this resistor. Now, the resistor is resisting the flow, but that's okay. The voltage is pushing enough that the electron, I'm the electron, gets pushed through this, and then it actually gets to this guy, and it gets pushed through that as well. But as far as the electron's concerned, it really sees this as one load. It doesn't know that there's a wire connected from here to here that has high conductivity to it. It's really not aware of that. It just sees it as one load, or one big resistor. And that's how we actually find the total resistance, is that we look at all of the resistors in series as though they're one big resistor. So let's just say the resistance of my light is RL, and the resistance of this is R1 because it's R1. So this Kirchhoff, pretty cool dude, he unpacked all of these circuits. So what we do is we take a look at Kirchhoff's laws, and there are a couple different things that he looked at, but one of them was that the resistance here plus the resistance there equals the total resistance. The other one was actually pretty cool, was that the voltage drop across that plus the voltage drop across this equals the voltage source. But let's just walk through like the total resistance formula. So if we take a look at that, we can say RT, in this case, I'm making out my formula here. RT is going to be R1, the resistance of R1 plus the resistance of the light. So that's going to be whatever it's going to be. I haven't put numbers here yet. We won't play with numbers just yet. We also know that there's a voltage drop across this and a voltage drop across that. So we're going to call that, the voltage drop across here is VR1, and the voltage drop across here is VRL. It just so happens, Kirchhoff figured this out as well. He said VS equals the voltage drop across R1 plus the voltage drop across RL. Doesn't ever get L. But, I mean, if these were just all resistors, it would be R1 plus VR2 and then plus VR3. Even if you had 100, the voltage drop across each would equal the total voltage, the source voltage. So, with all that said and done, we can then throw some numbers in here. Let's say that's 10 volts. So my source is 10 volts. Let's say my R1, equals 100 ohms, and R2 equals 100 ohms. So really nice, basic, simple numbers. Because they have the same value of resistance, they actually do the same thing as far as dropping the voltage. So the voltage drop across this is going to be equal to the voltage drop across this. And we know the two of them are added up to 10, so obviously the voltage drop across that is 5 and the voltage drop across that is 5. So if we also threw some total numbers in here, we already have these numbers here. So we can say that this is 100 plus 100. I'm going to put a bracket here and say ohms, because I know I have to do the math with the units. They have to be represented. I can say 100 ohms plus 100 ohms, but it saves me from drawing the ohm symbol twice. Sometimes they get really complicated. Just do that. And that's obviously 200 ohms. That's very good ohms. So if we take a look at this guy, we're going to say that the voltage drop across that plus the voltage drop across that equals that. But how do we actually know that the voltage drop across this is 5 volts? I mean, we kind of know that because they're dividing them up evenly. But what if that was like 67 ohms and that was 327 ohms? How would we know how they divide up the voltage? Well, there's something called the voltage divider rule, but I don't want to get into that right now. I want to get into something called Ohm's law. Yeah, it's pretty cool. So Ohm did some pretty cool stuff. Kirchhoff did some pretty cool stuff with circuits as well. But what Ohm did, he did this. We understand the nature of voltage is the energy per coulomb, and we understand the nature of current is the actual charge, the coulombs per time, and the resistive thing is actually linked to these things. But let's actually put them all together and see how they all fit together. This voltage concept, current, and resistor. Ohms came up with this, and he said V equals I R. Yeah, Ohm's law, pretty big deal. So if we actually wanted to know the voltage drop across this, we could do this. But wait a second, we don't know the current. How do we know the current? Well, I think the first thing we need to do is we have to calculate the current. And that's another concept of a series circuit, in that current actually is the same in all places in the circuit. We'll take a look at it. You're the resistor. Actually, you're the resistor. You're the electron. Not just one, but you're like the coulomb. You're like all of these electrons. And you're buzzing through this circuit. And you're here, and then you have to go here and here and here. I mean, your whole purpose in life is to go from the positive to the negative, but not really. But conventionally, that's how we look at it. So that's your whole shtick. You want to go from here to there. Any path, you'll take it. Even if there's resistance there, you'll take that path because the voltage is pushing you. There's that pressure behind you. So you've only got one path. So if I were to actually study the current right there, if I were to put a magnifying glass and study the current right there, it's going to be the same as the current right here, or even right here, or anywhere along the, if I studied the current anywhere, even in the middle of the light bulb, it would be the same. So I can actually use Ohm's law to find the total current, and then from there I can find the individual voltage drops across each one of these. Okay, so we know that Ohm's law is like this, but we can also use that for the whole circuit or any particular individual component in the circuit. Let's use it for the whole circuit. So we represent that formula a little differently. The reason it's different is because we specify what the name of each symbol is. So for the whole circuit, we're going to do this. We're going to take a look at IT is going to be Vs, the total voltage drop across everything, over RT. We know RT is 200. We calculated that earlier. So Vs is 10 volts divided by 100 ohms, and that's 0.05 amps. Kind of a weird number, 0.05 amps. It's kind of like saying, yeah, how long is a building? Oh yeah, it's 0.05 kilometers, when really it's just 50 meters. So what we do is we use a metric prefix. I'm going to say, or 50 milliamps. Now, that's a number we talk about. When we actually do the mathematics, we have to use this number. So now that we know the total current through here, through here, through here, we at any point can say this. We can say IT is going to be equal to hold on a sec, IR1, which is also equal to IRL. So now we can use Ohm's law using different symbols, and we can take this guy and study just the voltage and the current and the resistance right there, or just right there as opposed to the whole circuit. So I want to find the voltage drop across that guy. Let's use Ohm's law. So again, I'm going to write this with my symbols specific to what I'm talking about. So that's VR1, and I know that's V equals IR. Okay, so it's IT, but it's also IR1 times R1. So in that case, I know it's 0.05 amps times 100 ohms, and that is going to give me a value of 5 volts. So I know the voltage drop across that is 5 volts. And we can see that if I went ahead and I did the same math with the voltage drop across that, I'd just be using different symbols to some degree, but I'd come up with the same number. And we kind of looked at that, and it makes sense that if I'm starting with 10 and I lose 5 here, and remember the reason I'm losing 5 is because this guy, that energy is being lost, pushing the charge through here, so I have a voltage drop across here of 5 volts. Again, I'm going to have a voltage drop across there of 5 volts because I have 100 ohms here as well. I want to go on to something called Kirchhoff's voltage law for a series circuit. And that has to do with the voltage drops actually adding up to the total voltage. As you can see, 5 volts plus 5 volts equals 10. So this is what that looks like mathematically. So we say that Vs equals the voltage drop across R1 plus the voltage drop across RL, or it could be R1 plus R2 plus R3 plus R3, voltage drop across each. So in this case, it's going to be 5 volts plus 5 volts, which is equal to 10 volts. So we know that that's my Vs. So that's Kirchhoff's voltage law. As far as the other things go that I think that we need to talk about or kind of reiterate is that the current is the same in all points of this circuit because the current's only got one path. The voltage drops are going to add up to the total voltage. And if we want to know the total resistance that the current is resisted by, or I would rather look at it as though the resistance itself is drawing the current. So how much total resistance is drawing the current? We just add that plus that. Pretty straightforward. As far as anything else goes, we just want to look at maybe the fuse here and the nature of the resistance. I will reiterate this as well. I'll say that, the boss of the voltage is the voltage source. Often that doesn't change in a circuit. Whatever the voltage source is, it's there. But sometimes the resistive nature of the load changes. And I'll give you an example in this case. We have a light bulb here. I'm not sure if you know this, but if you were to measure the cold resistance of a light bulb, it would be lower than the hot resistance of a light bulb. What's going on here is that as any element gets cooler, its resistance actually decreases, and as it heats up, its resistance increases. So this 100 ohms here is of the working resistance of that resistor, of that light. But at first, that's only say 50. It's about half. So right at first, the total resistance is only going to be 150 ohms, which means the current's going to be higher because there's less resistance resisting the current, so it can flow more. So when we turn this on immediately, there's going to be like this spike in current, and we have to make sure that this fuse, now the total current we know is 50 milliamps. So I'm going to go and get like maybe a 70 milliamp fuse because I know at first when I turn it on, the current's going to spike up pretty high. And the fuse will have to be able to deal with those spikes. I think that's all we really need to talk about for series circuits, and I think we're good.